Hey everyone, my name is Nick Durish, and on Thursday, August 27th, I defended my master's in computer science with a specialization in human-computer interaction at the University of Guelph. Unfortunately, there was some technical issues and the defense was not recorded. So for all of those who didn't get an opportunity to attend, this is being recorded after the fact. Without further ado, this is a case study in the design and development of a community-based Internet Assessment Initiative in Rigolet, Nunatsiavut. Before we begin, I'd like to acknowledge that the work presented here has taken place on the homelands of the Inuit of Nunatsiavut and the Innu of Nitassinan, as well as the homelands of the Adawandran people and the Mississaugas of the Credit. This work would not be possible without the continued guidance, wisdom, and leadership of the Inuit of Rigolet. As a brief summary, the breakdown for today's presentation will follow the same format as my thesis document. First, we'll begin by providing a background on internet inequity and data measurement initiatives in Canada. Next, we'll briefly discuss the true purposes and motivations behind this research and what brought it all to Rigolet. We'll then explore the processes that occurred within this initiative over the last few years, and then dive into some of the results. Finally, we'll discuss the implications of this research and provide some recommendations for future work. Data transmission networks have become a nearly ubiquitous part of the modern world. What began as single data transmission streams turned into small niche networks that in turn converged, forming a globally interconnected network that we now call the Internet. The Internet is a hierarchical conglomeration of semi-redundant networks with no central governance. By 1990, there were approximately 100,000 computers hosting content on the Internet. By 2012, this number grew to over 1 billion. Today, I was able to wake up and use my computer to send this video stream through my local area network, into my regional network, into the regional data center, into the internet backbone, and finally on one of the servers or CDNs that is being used to host Microsoft Teams today. Then my data packet took a totally different path through to your device. And this is far more than just a convenience. For me, this means I can defend my thesis during a pandemic. But for others, this is an essential catalyst in creating opportunities, offering services, and accelerating standards of living. Research has shown that access to suitable telecommunication networks within communities can support local culture, healthcare and wellness, commerce, political involvement, and access to education. These benefits are in part why in 2016 the Canadian government identified broadband access as a fundamental human right for all Canadians. Specifically, they set a goal that by 2021, at least 90% of Canadian residences and businesses would have access to unlimited data, with 50 megabits per second download speeds and 10 megabits per second upload speeds. Well, 2021 is right around the corner, and do 90% of Canadians have access to these benefits? I'm not so sure. Due to the hierarchical and tree-like architecture of the Internet, it's far more powerful the closer a node is to its parents in the network. While this configuration has been cost-effective and serviceable in urban regions, it's also prone to bandwidth bottlenecks, an inequitable distribution, and single points of failure. Networks that exist at the fringes of the Internet are called last-mile networks and are particularly prone to these issues. Unfortunately, three of the factors considered most by Internet service providers and governments alike when they're erecting new network infrastructures are population density, economic or industry incentive, and ease of access, meaning remote and northern communities are often the most marginalized. And perhaps the most remote and certainly the most northern you can get in Canada is Inuit Nunatsiavut. Inuit Nunatsiavut is a subsection of Inuit traditional lands spread across 4 settled land claim regions. Inuit Nunatsiavut accounts for 35% of Canada's landmass and 50% of its coastline. The Nunavut Implementation Commission said that they embraced the Internet as a community development tool and see only positive implications for Inuit society. But despite this, the region is still comparatively underserved. I don't expect this inequity to come as a surprise to many of you. However, I do hope a few questions have popped into your head. Namely, how do we qualify or quantify such an inequity? How large is this inequity in Canada and who exactly is affected? And how can we use our understanding of this inequity to work towards closing the gap? Thankfully, research on the digital divide has narrowed its sights exactly on these questions. The digital divide is the gulf between those who have ready access to computers and the Internet and those who do not. While the term is decidedly broad, For the purposes of this research, we'll be focusing solely on access to broadband and broadband speeds in particular. Despite the amount of research focused on the divide, there is still a lack of empirical evidence or data to answer our deeper questions. The most commonly shared statistic to represent the digital divide in Canada was released by the CRTC in 2016 and reported that 100% of households in urban regions had access to download speeds of at least 5 megabits per second. That was compared to 87% in rural regions. There are conflicting views, however, on the validity of these numbers. One thing is clear, though. Out of all of the potential approaches to bridging the digital divide, which include increasing public awareness and regulation, as well as investing in data transmission and network innovations, would all benefit from an increased understanding of internet inequity. To aid in this understanding, we can leverage data transmission measurement tools. These tools perform diagnostics by uploading a test file to a pre-configured server and collecting relevant measures. These are usually at least the download and upload speed in megabits per second, as well as the round-trip time, which measures the time to send, process, and get a response from a packet. These tools can also measure other heuristics such as latency, jitter, ping, or packet loss. The most widely used data transmission measurement tools include Speedtest CLI, Network Diagnostic Tool, and iPerf. If you've ever tested your internet speeds, you've been introduced to these tools before. Speedtest CLI is owned by Ookla and runs on speedtest.net, which is where the screenshot on the left is from. The screenshots were taken yesterday within moments from each other. The screenshot on the right is from Google's Speedtest running NDT. NDT is owned by MLab and also used by the CIRA. iPerf is an open source and a highly configurable tool. However, unlike these other tools, does not have a graphic or browser-based interface and can be a bit more complicated for non-technical users. These three tools are by far the most popular measurement tools. However, there is also hundreds of other alternatives available. But why so many? And on that note, why are the results from the two most popular measurement tools different when tested within seconds of each other? Unfortunately, not all data transmission measurement tools are created equal. On top of using different measurement protocols, they can be tested based off different server configurations. Some tools, such as Speedtest CLI, test on on-net servers, which exist within the infrastructure supplied by the ISP, whereas some, such as NDT, test on off-net servers. However, even if two tools used off-net servers, they could be located at drastically different points, causing variation in measurements. And even if they were in the same location, networks can be fairly dynamic, and packets may be routed differently depending on when they're tested. User hardware also plays a role in a speed test, as many devices have limited network bandwidth capabilities. These disparities between single measurements are emphasized when they're collected and compiled into entire datasets by measurement initiatives. This table displays the reported statistics of popular measurement initiatives for the second quarter of 2019, and as you can see, they can't seem to agree on what the internet looks like here in Canada. In all three of these initiatives, the tests were performed actively, meaning a user had to initiate a test at the time of their choosing. Passive tests are performed automatically and produce far more accurate results. By simplifying complex data into a single mean value, these initiatives have also lost some of the nuances of their data, and in some cases even misrepresented it. For example, research has shown that the internet speed distribution in many regions follows a multimodal distribution, in which the mean is a poor reflection of the central tendency. Finally, the initiatives also make little effort to perform proper sampling. They allow any individual to add any number of points to the dataset any amount of times. This can drastically skew results and underrepresent areas with less testing. For example, while Nunatsiavut's population accounts for 0.007% of Canada, the CIRA dataset contains only 43 measurements for all of Nunatsiavut, or 0.00005% of the total measurements, which is over an order of magnitude less representation. These inaccuracies can have some significant real-world consequences. This is a map maintained by the CIRA of their dataset, which classifies 25 kilometer squared areas as served if at least one household had access to speeds of 5 megabits download. Served locations are ineligible for some federal funding. However, when the regional county municipality of Montcalm found themselves on the served list, they did a detailed private study and were able to provide evidence that they were indeed underserved, regaining their eligibility for funding. There is a clear need for more measures of the digital divide, and in 2019, the Standing Committee on Industry, Science, and Technology officially broke down that need further. There is a need for more small, rural, and collaborative initiatives that focus on in-depth analyses within specific regions. There's a need for datasets that use a variety of measures and methodologies to reduce known gaps and discrepancies in data transmission heuristics. And there is a need for full datasets with extensive metadata that consider not only measures of internet performance and access, but also indicators and correlated variables. So we've explored the greater value and need of a community-based internet assessment initiative. But what truly is the Rigolet Internet Assessment Initiative, and what brought us there? The small Inuit community of Rigolet is located in the circumpolar north at the entrance of Hamilton Inlet and is the southernmost of the 5 Inuit communities in Nunatsiavut. It is accessible via snowmobile, dog sled, boat, or a 45-minute flight on the Twin Otters aircraft from Happy Valley Goose Bay. The community members of Rigolet share a rich culture and they foster a strong relationship with their surrounding lands. The community has also been actively exploring the use of technology to support traditional activities. The My Word Storytelling and Digital Media Lab was created in 2009 to gather place-based narratives. The community also partnered with researchers from universities including Guelph to explore the use of community-based health and environment monitoring system entitled Inuit, and was previously involved with Left.io, a company in Vancouver, in the exploration of a mobile mesh network in the community. However, Rigolet lands within last mile network, and the community members often report slow and inconsistent internet service. This not only impacts their ability to adopt new information communication technologies, but as previously mentioned, reduces their equitable access to the benefits and services that many other Canadian communities enjoy. If their speeds are low enough, this inequity could be an infringement of their fundamental human rights. Unfortunately, as of 2017, before the beginning of this research, there existed 0 publicly available internet measurements for Rigolet. And that's where the Rigolet Internet Assessment Initiative comes in. The motivations were first to contribute to an increased understanding of telecommunication networks within Rigolet, to provide the community with tools and support to develop their own ICTs and to support their efforts to increase internet speeds and access, whether that's through their own research, development, or regulation. The second motivation is to support the Standing Committee on Industry, Science, and Technology's needs for overcoming the digital divide. And to achieve these broad motivators, the Rigolet Internet Assessment Initiative was set up to achieve 2 broad goals. 1, build an extensive and interoperable telecommunication network assessment dataset for the community of Rigolet and to perform some preliminary analyses. And 2, to build and reflect upon a process to leverage measurement tools in small Inuit-led and community-based measurement initiatives. This includes a process with the community, as well as building the necessary data collection system. The way we went about this can be broken up into 6 distinct phases, which will be discussed further within this section. The methods explored here took place over an extended period of time between August 2017 and March of 2020. Before stepping right into our research investigation, we formally highlighted some considerations. The first was participatory design methods, which involve the cooperation of users and stakeholders from all facets of the design process. PD methods lack a distinct framework and instead emphasize the use of mixed tools and techniques. This was well suited for our research, given the pre-existing knowledge among community members. Our use of interviews, open houses, and open discussions were largely based out of this consideration. The second consideration was to leverage some of the frameworks from the Agile Manifesto, namely to focus on individuals and interactions over processes and tools, and on software over documentation. These paired well with PD methods and allowed us to develop in quick bursts, such that we could begin prototyping a bit quicker. Finally, and perhaps most importantly, our research heavily considered the Inuit Tapirut Kanatami's National Inuit Strategies on Research. In consideration of these strategies, we kept community members as the guiding force. Ethical research approval was granted from both the University of Guelph as well as Memorial University, and formal research approval for the analysis and publication of this research was provided by the Nunatsiavut Government Research Advisory Committee on July 22, 2019. This means that all data prior to this date has been omitted from this publication and presentation. Volunteers retained the rights to revoke their data at any time, and the Rigolet Inuit community government acted as a co-owner of all data collected. The Nunatsiavut government reserved all control and governance over the use and distribution of the data. All funding for the project was gathered through outside sources and used for purposes with benefits to both the project and the community, such as hiring a paid community-based research lead, who, though won't be named here today, was hugely involved throughout this research. The first phase of the design process was focused on establishing a foundation within the community. Our team conducted 3 open houses and over 40 bi-weekly consultations with our community-based research partner, as well as several informal observations and conversations. Within these activities, we discussed the research, provided updates, and posed some questions. Namely, what are some of the ways of describing internet access and speeds in Rigolet? Is there anything recognized as indicators of internet speeds in the community? And is it common for community members to own internet-connected personal devices? It was also important that our team engage in the community's local culture, events, and activities. We found that through focusing efforts towards building relationships, we were better equipped to design an initiative that was valuable for and easily used by the community at large. Some of the events that we participated in included the Rigolet Salmon Festival, teaching computer classes at Northern Lights Academy, and teaching comp sci skills at the Rigolet Summer Science Camp. The second phase was to take our knowledge from ideation and to begin building a broad design for the measurement system. We needed to collect longitudinal data from multiple locations within the community. That would require utilizing some hardware to run a data transmission measurement tool. Based off our literary research, we opted to use custom hardware running passive tests. The test would at the very least need to collect the download speed, upload speed, and RTT, as well as the metadata. Feedback from community members in Phase 1 emphasized the importance of security as well. So the devices supported automatic security updates, secure shell was turned off, and the devices were inaccessible outside their network. The data would then be sent to a cloud-based storage solution with co-ownership of the directory shared with every volunteer. Community members were eager to have access to their data, so to aid in this interpretation, we chose to pull data weekly to be analyzed and disseminated. While in Rigolet in August of 2017, a custom PHP script was loaded onto a microcomputer called a Raspberry Pi. This ran the iPerf tool to record upload speeds, download speeds, and RTT every 10 minutes. The records were then sent to MySQL database on Amazon Web Services. Unfortunately, the device ran into several issues, reported some false positives, and required a degree in computer science if you wanted to access the data. This was retrospectively dubbed version 0.1, though it was probably less of a version and more of the inciting project for the initiative at large. In July of 2018, we returned to Rigolet with version 0.2 and more of a plan. Instead of iPerf, this version utilized Speedtest CLI configured to a test server in St. John's. We also switched from Wi-Fi to a wired connection with a Cat5 cable. This version solved many of the instability problems. However, I soon realized that on some occasions, during slow periods, the device was unable to upload and therefore lost some of its records. By August of 2018, I'd completed the next iteration which fixed the lost records issue by saving test results within a .csv file and attempting to upload the file once a day at 3 a.m. This had the added benefit of reducing network load in the community. This version also switched to utilizing Dropbox as the primary upload server. This was due to its free tier cost and ease of access for less technically inclined users. 2 devices loaded with versions 1.0 were left running within the community. By March of 2019, it was clear that this iteration was performing very stably, and 10 more devices were loaded up with version 1.0. The final hardware used for the devices were Raspberry Pi 1 Model Bs, donated from the University of Guelph School of Computer Science. The 10 shiny new tester kits were delivered to our community-based research lead in March of 2018. He then reached out to the community, and 8 households volunteered to participate in our case study. On April 6th, I updated the 2 test devices that we had been using in the community to the most recent version of the software, namely switching from our test database to our production. On April 8th, 8 monitors were installed in our volunteer households by our research lead. Volunteers were provided a $50 gift certificate to the local shop and a pamphlet with information on research initiatives, my contact details, and how to access their data. In the first week of June, one tester had its SD card fail, and another tester died for some unknown reasons. These testers were replaced by 2 extra devices that had been left in the community specifically for this purpose. Unfortunately, during the second week of August 2019, an electrical storm passed over the community and wiped out 3 of our testers along with many other household devices. To provide participants with consistent updates of their data, the RIAI Disseminator tool was implemented. The software ran on my home server once a week, which initialized a bash script to pull updated data from each respective Dropbox directory. It would then compile and clean each data record in a dataset and remove information which could be used to identify volunteers. This data was then sent to a Python script and transformed into a dynamic, interactable graph using the Plotly graphing library. This was output as an HTML file and automatically uploaded onto a website with a custom subdomain for each tester, which was hosted on GitHub pages. The example shown here is the output from the control tester, which was running at my home throughout the research. The final phase in our methods was to perform some preliminary analyses on our new dataset. First, we had to cleanse and compile the dataset. Then Python's math library was used to calculate a variety of summary statistics, and normality tests were then performed to help select appropriate central tendencies. The second type of analyses was of explanatory variables, in which we used a univariate linear regression test against external data. I performed regression tests using the best normalized package within R, which output p-values allowing me to test against the null hypothesis that the variables are not statistically significant in predicting the criterion. For non-rejected variables, the beta value could then be examined to see whether there was a positive or negative influence. However, the effect of these variables on speeds was not investigated any further. For categorical variables, a pairwise regression analysis was required, which involves the selection of a reference term. Within the temporal analysis, I first examined the effect of time of day and then end of day of week on download, upload, and RTT. The environmental analysis was based on the community members' recommendations that weather and climate seem to affect the internet speeds. Unfortunately, with no publicly available weather data set for Rigolet, we had to average the data from Makovic, which is approximately 112 kilometers north of Rigolet, and Cartwright, which is around 107 kilometers southeast. The data sets from these communities provided the temperature, humidity, and wind speed. Once they were added to our data set, these variables could be analyzed in a similar fashion to our time data. Finally, we come to the results. And like the goals of the initiative, these can be broken up into 2 main sections, the process and the data set. For the process, our consideration for the ITK guidelines helped to better tailor tools and methods for a remote Inuit community. They resulted in a process which shifted the direction of our research towards community recommendations, such as continuous dissemination of data, increased security, and analysis of environmental indicators. It guided us towards working along closer with Nunatsiavut government to ensure ethical practices in our research, and it also played a role in guiding the ownership and control of our data. Our consideration for PD methods reinforced our ability to work with community members and stakeholders, and provided guidance for communication methods such as open houses and interviews. Agile methods allowed our team to focus on software and testing over documentation, and allowed for quick development sprints when necessary. And another result from our process which shouldn't be overlooked is the software suite. It consists of 3 separate and largely automated software libraries for testing, disseminating, and analyzing the data like in this research. The code is all available on my GitHub account for use or modification by anyone who's interested. The more concrete results of this research, however, is the dataset. In keeping aligned with our ethics approval, the dataset used within this publication begins on July 22, 2019 and ends on November 19th. It includes data from 6 separate test devices totaling in 9,436 records. Within these records, the mean download speed in the community was found to be 1.38 megabits per second, and the upload speed was 0.55. In total, the dataset contained null entries for 0.93% of all measurements, meaning the internet was down in the community almost 1% of the time. The two graphs on the right here depict the data stream from each tester of the analysis period, as well as their geometric mean. You will notice some notable trends. First of all, you'll find that all of them follow a fairly similar pattern. This is to be expected as they are all subsets of the same internet function within the community, though they are also all slightly diverged. This could be, for example, the orange line here is consistently above for the download speeds compared to other households, and yet for upload speeds is consistently below. This could be due to how the wireless network within their household is configured, or simply where they exist within the community. You'll also notice the longest period without connectivity in the community was on October 18th, and it lasted for 14 hours. That can be seen as the large spike here. That brings us to analysis of explanatory variables, first being the time of day. We started by generating some box plots with the measurements over each hour of the day to observe any trends. And indeed, a trend does seem to appear. It looks like for all measurements, the internet speed increases slightly around midday. You can see that on almost every graph here. And for download speeds, it appears that there even might be some sort of waving pattern here, with speeds increasing slightly around 5 a.m. and 10 p.m. And the results of our regression analysis agree with this observation. Indeed, for download speeds between 5 and 7 a.m., 10 a.m. and 2 p.m., and 10 to 11 p.m. were found to be statistically significantly different relative to midnight. For upload speeds, 10 a.m. to 2 p.m. were found to be statistically different, and for round-trip times, no trends were found, which may be attributed to the higher values in diversity in RTT measures. In general, however, these results seem to indicate that speeds may be slightly quicker from 10 a.m. to 2 p.m. daily in Rigolet. The next explanatory analysis was day of week. From our generated box plots, there was no trends that appeared obvious, except for perhaps that download speeds appears to be slightly faster on Saturdays. We also generated these calendar breakdown plots to observe any patterns that might be occurring in the day of week column. Generally, no trends are too obvious, although for the column of Saturday for download speeds, it does appear that it could be slightly darker on average than other columns. However, our regression analysis is able to provide more nuance than this. For download speeds, Saturday, Sunday, and Monday were found to be statistically different when compared to Wednesday, and for upload speeds, Saturday was found to be statistically different. From these results, we cannot reject the possibility that internet speeds are slightly faster on the weekends, particularly Saturdays. The final examination was of explanatory variables that were environmental. As we had to collect and average these data, the summary for the temperature, humidity, and wind speed can be seen on the table at the top. To aid in our visual observations, we generated the calendar breakdown plots to compare with the previous calendar breakdown plots. Although from our observations, it's very difficult to see any trends relating these variables to internet speeds. However, our regression analysis is able to provide a bit more detail. For download speeds, neither temperature nor humidity could be rejected as being non-significant. For upload speeds, neither temperature, humidity, nor wind speeds could be rejected, and for RTT, all environmental variables could be rejected. However, in general, we can't reject any of the environmental variables as having some potential impact on the internet speeds within the community. As previously mentioned, before the beginning of this research, there existed no publicly available data on internet speeds in Rigolet. Since then, however, 3 new data points have been added to the CIRA internet speed map. They average 1.25 megabits per second download and 0.45 upload. These are actually slightly lower than our measures, but given CIRA's use of NDT, which uses off-net servers, this is actually to be expected. Now, however, there are 3,145 times more internet assessment records for Rigolet to utilize as they please. Based on our results, compared to the 2019 Q3 speed test report, Rigolet's mean internet speeds were 81 times lower than the average Canadian. That means it would take someone in Rigolet over 2.5 months to download what most of us can download in a single day. The software tools and description of our process are also available for the extension of this research. Should work continue on RIAI, or it be expanded or translated in other communities, there are some notable improvements in both the process and the data that should be considered. Most notably, we utilize speed test CLI for its stability in our pilot phase. However, the addition of a second speed test, namely NDT, would allow us to better integrate our data into the CIRA and MLab datasets, and it would help with comparative analyses to other initiatives. More metadata would also help to steer the interoperability of our dataset, allowing it to be leveraged more easily for other research. The inclusion of more explanatory variables in our dataset and getting some more accurate weather data would enhance the analyses that could be performed and may allow more nuanced results to be extracted. And finally, the expansion of our sample size will capture more assessments and provide more accurate representation of the internet. This could be through increasing frequency of the measurements, increasing the number of participating households, or increasing the length of time the study runs for. There's also some improvements to be made to the process. By performing a more in-depth analysis of our dataset, we can extract more valuable information on speeds and maybe even begin to model them. These analyses could include interactive variables, threshold variables, multivariate analyses, or geospatial analyses. We could also make updating and deploying test devices much simpler. By leveraging software provisioning and deployment tools such as Ansible, we can have devices securely pull updates whenever necessary. By including other measures of access such as cost or hardware availability, we can begin to capture a more qualitative view of the digital divide as well. There's also hardware upgrades. First of all, surge protectors would have saved our 3 Pis from their electrical tomb, but also by upgrading our hardware from Raspberry Pi 1s, we can capture measurements greater than 100 megabits per second, which would allow for more appropriate control measures and deployment in urban regions. And finally, as I transitioned deeper into performing my analyses, writing my thesis, and completing my master's late in 2020, I became much less involved in reaching out to volunteers. And in June of 2020, there was only 2 devices left in Rigolet still uploading data. It's more than possible that without my monthly updates and involvement, these devices were simply unplugged. And if the community or volunteers wish, they can be plugged back in at any point, and any data will continue to be collected and disseminated. For the longevity of a project like this, however, it would be beneficial to have a representative for the initiative that's available for maintenance and to consistently check in with volunteers. There is still so much work that can be done. On top of extending this research, the resulting dataset can be leveraged for a multitude of uses, from supporting ICT development to aiding in public awareness and regulation. In general, though, the Rigolet Internet Assessment Initiative does not present itself as a vehicle across the digital divide, but a step towards its closure. Only through increasing our understanding of data transmission speeds, access, and distribution can we implement informed strategies for internet equitability. Thank you, and nakumek. And I have far, far too many people to thank here today. I'm not going to name all of you, but thank you so much to my advisory committee, to my fellow researchers, the government representatives that were helping along the way, my wife, family, and friends, and of course, more than anyone, the community traditions and lands of Rigolet.